So today we are going to start talking about amplifier circuits. Introduction to JT. Amplifiers. So transistors in general are utilized in two different broad application ranges, right? They can be used as switches in digital circuitry, and they can be used as amplifiers in analog circuitry. For the most part, in the amplifiers that we're going to be looking at in this class, these are going to be small signal amplifiers. So voltage amplifiers less so than power amplifiers, okay? So let's consider this circuit. We have our power supply voltage VCC, a resistor RC, we have a BJT here. This is going to be our ground at the bottom. And we are going to take our output voltage plus minus here between our collector and emitter terminals. And over here on the left-hand side, let's put a DC bias voltage, capital VBE. And let's perturb this system. Let's mess with it a little bit and see what happens, okay? So I'm going to call this perturbation voltage lowercase VBE. And since those two voltage sources appear in series, I'm going to call this voltage, the sum of them, lowercase v capital BE. I'm going to call this current lowercase I capital B, this current lowercase I capital C, and this current lowercase I capital E. Okay. So let me explain what I mean by all these lowercase and uppercase jibber jabber right here, all right? Because I'm sure it's going to be confusing because we're using the same letters over and over and over, okay? So if I have a quantity that is in all capitals, so both the quantity itself, like VBE here, where the V is a capital letter and then the B and the E are capital letters, this is representative of a DC quantity, okay? If I have a quantity that is all lowercase letters, like this VBE, it is representative of a small signal, and we'll just explain what that means in a moment, AC quantity, okay? And then if I have a mix, so here for IC, IB, this VBE, and VCE, I have a lowercase quantity and then uppercase subscripts. What that means is that I'm looking at a mix of a DC quantity with an AC quantity superimposed on top of it. Okay, so all capital letters, DC quantity, all lowercase letters, AC quantity. If it's a mix of AC and DC quantities. Are we talking at least the same language here? Maybe not on the same page, but at least talking the same language. All right. So CE is uppercase, V is lowercase. Yeah. So what we're going to do here is we're going to look at this circuit ignoring the perturbations, which just makes this a simple DC BJT circuit that we need to determine the DC bias point of. And then we are going to see what the perturbations do to the bias point and what those effects are. Okay. So if we ignore lowercase VBE, all lowercases, the perturbation voltage, and we ignore the early effect, for this particular circuit, IC should be IS EXP VBE over VT. IB would be 1 over beta IC. IE would be beta plus 1 over beta IC, and our output voltage VCE would be VCC minus IC RC. Anybody have any problems with literally any of these relationships? They should be old hat at this point, okay? So this is telling us what the DC operating point of the system is for a particular VBE. And in this case, we don't need to solve for VBE or anything. It's literally just a controlling voltage, right? By the way, this is not even close to how you actually set up an amplifier circuit, but it's going to help us figure out what the heck's going on. All right, so if we include the perturbation, lowercase VBE, we should see that lowercase I capital C becomes IS EXP capital VBE plus lowercase VBE, all divided by our thermal voltage, right? So if we move a little bit beyond our DC biasing point, we should expect our collector current to change a little bit, right? Well, when I have two exponential functions, excuse me, when I have an exponential function and the argument of the exponential function is a sum, I can break this into two exponential functions, right? So I can say that this is IS EXP capital VBE over VT multiplied by EXP lowercase VBE. Let me make that V smaller. Over VT. And recognizing that IS times EXP capital VBE over VT is just capital I, capital C, or our DC bias collector current. This gives us IC times the exponential of VBE over VT. So, I'm going to go back to some old school calculus for you guys here. We're going to do the Taylor series expansion of this guy. But we're only going to look at the first two terms. Okay, how many of you guys remember what the Taylor series expansion of an exponential function is? Hayden, what is it? So if you have e to the x, it's 1 plus x squared over 2 factorial plus x cubed over 3 factorial, et cetera, et cetera, et cetera, right? So we're going to put a constraint here, all right? For lowercase VBE less than VT. So typically speaking, VBE needs to be smaller than 10 millivolts or so for this to be true. EXP VBE over VT looks like 1 plus VBE over VT plus the higher order terms, which we're going to throw away, because when VBE is much smaller than VT, those are just getting progressively smaller and smaller and smaller and doing less and less and less. Okay. So from this, we can say that lowercase I, capital C, is our DC bias current IC multiplied by 1 plus lowercase VBE over VT, or capital IC plus capital IC over VT times lowercase VBE. So our collector current contains a DC bias component and a small signal current that is dependent on the value of the perturbation voltage and that ratio, capital IC divided by our thermal voltage. The small signal current, lowercase I, lowercase c, is then capital IC divided by VT times VBE, or what we're going to call G sub M VBE. This quantity G sub M is what's known as the transconductance. In this case, obviously given by IC over VT. Generally speaking, it is the change in the collector current due to a change in the base emitter voltage evaluated when lowercase I capital C is equal to the DC bias collector current. Okay. You don't have to remember this partial derivative relationship literally at all. It's simply IC over VT and you're good to go. Okay. This transconductance effectively tells us how good our BJT circuit is at converting an input voltage, lowercase VBE, into an output current, lowercase IC. All right. So we have, or the transistor in and of itself effectively behaves like a small signal transconductance amplifier, where it converts some variation in input voltage to a variation in output current. If I can scroll up here real quick, what we'll find is that the inclusion of a load resistor here converts that transconductance amplifier into a voltage amplifier. Because our output voltage is dependent on the quantity VCC minus IC times RC, well, the voltage drop over that resistor RC changes as that small signal collector current changes. So it's going to give us a voltage at the output that's superimposed on top of that DC operating point. Jordan. Okay. Are we talking about in red?
No. What we after the triangle.
This one is a lowercase c. Yeah, so the small signal collector current. Yeah, the C's are going to be the biggest pain in the ass today. So I'm trying to physically draw them large for uppercase and small for lowercase, but I'm happy to distinguish between the two as is necessary. Okay. So let's look pictorially at what the transconductance represents. All right. If we have a plot of lowercase I, capital C, as a function of lowercase v, capital BE, should look something like this. Let's arbitrarily call this point right here our bias point. So this is, let me put it on the other side here, actually. This is our quiescent operating point, or our DC operating point. This quantity is capital VBE. This quantity is capital IC. The transconductance simply represents, if I could draw a straight line here, our slope. And trying to draw some boundaries here. This green curve represents lowercase VBE superimposed on top of our DC operating point. Then this guy represents lowercase I, lowercase c, or change in our collector current. So this graph literally depicts exactly why amplification occurs. And we can plot VCE and effectively see that it's just going to be a larger version of the VBE signal. And depending on the configuration of the amplifier, it might be inverted, it might not. And we'll talk about all that bit later. Okay. So to this point, we have effectively just been talking about our transistor's ability to generate some small signal current at the output, right? So if we're relating things to a model, and that's exactly what we're going to do in a moment, we have shown that our BJT should have a voltage controlled current source between the collector and the emitter terminals. So just like we had in our large signal model, except that the value is slightly different. Now we're just going to have the current is GM times VBE instead of having that current be IS EXP VBE divided by VT, right? We're linearizing our nonlinear model for small perturbations. That's the whole point of these small signal models. Okay. Well, the perturbation signal lowercase vbe, since it causes a change in the collector current, it has to also cause a change in the base current, because the base current and the collector current are proportional. Okay. So I think there's enough room I can fit it in right here, actually. Lowercase I, capital B, is lowercase I, capital C, divided by beta. Literally has to be for BJT, right? This is, sorry, equal sign, not plus sign, the same as our DC collector current divided by beta plus 1 over beta times IC over VT multiplied by VBE. So we see that our base current has both a DC bias point as well as a small signal value superimposed on top of it. And from that, the small signal portion of the base current becomes 1 over beta IC over VT VBE, which is the same as GM divided by beta VBE. And so I want to stop here and talk for just a second. For our large signal model, for our BJT, what did we see between the base and the emitter when our device was operating in the active region, the forward active region specifically? You guys have notebooks. You presumably have been taking notes in this class for at least 6 weeks at this point. Large signal model of a diode. Excuse me, large signal model of a BJT. I literally just gave you the answer. It's a diode, yes. What was a small signal model for a diode? Those of you who didn't miss this question on exam 1. Little resistance. Small signal model for a diode was a resistance. Okay. So we're going to model that diode between the base and the emitter by the change in the base emitter voltage, or the small signal base emitter voltage, divided by this small signal base current, right? Because the base current is what's flowing through that diode. So we can say that R pi, I don't know why they call it R pi, so I'm just going to say that right out of the gate, is defined to be VBE over IB, or beta over GM, or VT over IB, or beta VT over IC. All of these literally give the same result. Okay. So we now have enough information to develop our small signal model, because we know what these perturbations are doing or what influences they're having on our system. Okay. So our small signal model for our BJT is going to look like this. Here's our base terminal. Here is our emitter terminal. Here is our collector terminal. Between the base and the emitter, we have that resistance R pi. And then we also have the voltage drop over R pi is our small signal voltage VBE. Some textbooks call this voltage V pi. I'm going to try to be consistent and use lowercase VBE throughout, but if I slip up and I write down V pi, I literally mean the exact same voltage. And between the collector and the emitter, we replace our dependent current source with a different dependent current source. This one has a value of GM times VBE, where GM is equal to IC divided by VT, and R pi is equal to beta over GM. Okay. So I want to be clear here. The DC operating point of our circuit defines what these quantities are. Where we're at along that curve in the active region tells us if we're going to have a low transconductance or a high input resistance or something like that. Okay, so the biasing point is critical to the behavior of our circuit as an amplifier. Okay. Now, to this point, we have neglected the early effect. Let's talk about what happens when we include it. Okay, and it's really not that big of a deal. Okay. So when early effects are present, lowercase I, capital C, changes due to perturbations on lowercase VCE, right? So if we have a change in the collector emitter voltage, we should see a change in IC. We can model this. So let's put with early effect. We can model this as a small signal resistance, R lowercase o, because it appears effectively at the output of our amplifier, is the partial derivative of lowercase I capital C divided by the partial of V capital CE evaluated at some constant base emitter voltage to the -1 power. And I'm not going to make you suffer through the math there. This resistance is simply VA, the early voltage, plus VCE over IC, or it can be expressed as VA divided by IC prime, where IC prime represents our collector current with early effect neglected. This is the one that we're going to use 99% of the time. Okay. Typically speaking, the generally accepted practice for determining amplifier quantities is usually to ignore the early effect in the DC calculation and to include the early effect in your AC calculations. Okay. So this output resistance occurs between the collector and the emitter. So we can update our small signal model to include it by doing this. Here is R pi VBE. This is our base terminal. Here's our emitter. GM VBE R not RO. Collector terminal, and then our relationships are GM is equal to IC over VT. R pi is equal to beta over GM, and R naught is equal to VA over IC prime. So like I said, the majority of the time, we're not going to include the early effect in our DC calculation. So it's just whatever IC that we have will get us there, at least good enough. It's all an approximation anyway. Right? Any questions regarding the development of our small signal model? All right. So what I would like to do now is show you an example of how we actually set up a BJT amplifier circuit, and then determine those small signal parameters before we jump into amplifier analysis. All right. So let's say that we have the following circuit. Let's say that this is 1.1 kilo ohm. This is 150 ohms. This is our resistor R1, 67K. This is our resistor R2, 33K, right? So this is our DC portion of the circuit. Typically speaking, we would couple an input signal through a coupling capacitor that I'm going to call CC1, and we are going to assume that CC1 is very, very large. Okay. So what I mean by that is that it's going to look like an open circuit to DC quantities, and it's going to look like a short circuit to our AC quantities. And we might have some signal resistance. Let's call this R sig. Here is our input voltage, Vn of t. It is very likely, at least for this particular configuration, to include an emitter capacitance, which we're also going to say is very, very large, so that it looks like an open circuit at DC and a short circuit at our frequency of interest. Then on our output side, we have yet another coupling capacitor. Let's call this guy CC2. It's going to be large for the same reasons. And then we're going to have a particular load resistance. And then our output voltage is actually going to be a combination of a DC signal with a superimposed AC signal on top of it. Okay. So this is what an actual BJT amplifier circuit would look like. When you guys take the lab next quarter, you'll be doing this effectively, but in slightly different configurations for slightly different amplifiers. We're going to talk about the purpose of this guy probably on Monday, but let's talk about this guy right here because I think that's pretty interesting. Why would we put a capacitor, or why would we capacitively couple our output voltage to our collector terminal here? Why wouldn't we just put the resistor there by itself? Anybody have any thoughts? So again, this is an open circuit for DC and a short circuit for AC. That is actually a reasonable way to think about it, but slightly different. So if we're in transition, if we're in like intermediate frequencies, so we're a little bit below where we want this guy to operate, or if we're a little bit above in frequency where we don't want this guy to operate, it absolutely does behave as a filter. But effectively what this guy does is prevents the load impedance from influencing the biasing point, right? So at DC, when this capacitor is an open circuit, the load is disconnected. But at AC frequencies, it actually winds up looking like it's in parallel with this 1.1 kilo ohm resistor, which I'll explain what I mean by that probably on Monday, right? So we have to use this coupling capacitor here to prevent this 2 kilo ohm resistor from influencing the bias point of our system. This coupling capacitor CC1 over here does a similar thing, right? So if we didn't have a coupling capacitor right here, let's say that our signal is very, very small, at a DC point when our VN is effectively turned off, this is a short circuit to ground, which means our base is effectively shorted out to ground. That's why we have to use these capacitive coupling methodologies to superimpose our signal on top. Okay, so that's how we get our input signal superimposed on the DC value of our VBE. This is how we get our AC value superimposed on top of whatever this collector voltage happens to be. All right, so how would we go about determining the DC operating point of this guy? So we want capital VBE and capital IC. First thing we do is literally throw away all the crap that's capacitively coupled because it's all disconnected. All of those capacitors act as open circuits at DC because they're capacitors, right? So really, as complicated as this thing looks, our DC analysis is just this guy. What is this? It's the full bias BJT network, which we, at this point, hope know how to analyze because A, you've had a homework assignment due on it for a couple of days, and B, you're being tested on it next Wednesday. So I very sincerely hope you can analyze this guy, all right? So if our transistor has the following parameters, IS is equal to 5 nanoamps, beta is equal to 100, and the early voltage is equal to 5 volts, we should have enough information to determine the DC operating point of this guy. We're going to neglect the early effect in our DC analysis and develop a small signal model, or at least determine what our small signal parameters should be, right? So how do I analyze this guy? What's the first thing I need to do? Find V Thevenin. Exactly right. So V Thevenin, capital H, is 5 volts times 33 kiloohms over 67 kiloohms plus 33 kiloohms, which is simply 1.65 volts. Then I need to know what RTH is. RTH is just going to be the 33 and the 67 in parallel, right? That's going to look like 22.11 kiloohms. And then I have my equation, right? So I know that VTH, which I know is equal to VBE plus RTH, which I know, plus 1 plus beta, or I know beta, bless you, multiplied by RE. All of that multiplied by 1 over beta IS EXP VBE over VT, which I can solve for VBE. And when I solved it, I got 349.851 millivolts. I got that both using my calculator and MathCAD, so I feel pretty confident about it. And from here, I know that IC, and I guess really this, we'll call it IC prime. I'm going to give up on using this prime notation probably literally the next time I write it down. But it's representing the collector current with the early effect neglected is IS EXP, the value that we determined for VBE over VT. And I got 3.489 milliamps. Now, the derivation of our small signal model parameters rely on the fact that this is supposed to be biased in the forward active region. So just for the sake of argument, I'm going to check and make sure that that's true. VCE is just VCC minus RCIC minus, sorry, beta plus 1 over beta REIC. And I get 633.020 millivolts. So let me ask you guys, am I in the forward active region? Yeah, VCE is greater than VBE, so I'm in good shape here. All right. So I have a are you raising your hand or stretching? What's up?
Are we ignoring the early effects until VA is equal to 5 because of the capacitor?
No, we're ignoring the early effect because it's a pain in the ass to calculate the DC operating point with the early effect. But that's literally the reason. It's a pain in the butt. Yeah. So like on an exam or something like that, I literally couldn't ask you to do it because it involves setting up a system of equations that your calculator cannot solve. So I will be very explicit on your homework questions, whether or not I want you to ignore the early effects in the DC calculation or not. But generally speaking, you ignore it in the DC calculation. So now that we have a well-established DC operating point, we are good to go in determining our small signal parameters, right? So our transconductance, IC over VT, is 134.208 millisiemens, or we could call that milliamperes per volt. We felt like it. R pi, which is beta over GM, is 745.114 ohms. And RO, which is VA over IC prime, is 1.433 kilo ohms. And then we would be off to the races with amplifier analysis once I teach you guys how to do the amplifier analysis part. Okay. All right, so let's start on that amplifier analysis, but do I need to go back for people to continue to write stuff down or everybody? Okay. All right, so there are three very basic BJT amplifier topologies. Right. So the first of which is what we're going to call the common emitter. Now, what I'm about to draw is a very, very simplified version. So this is not remotely what the actual common emitter, or in a couple of minutes, common collector or common base amplifiers look like. This is just going to serve as our jumping off point for figuring out how these things work, and we're going to work our way towards the amplifier with the full bias network and see what the effects the biasing network have on the amplifier itself. Okay. So our common emitter amplifier looks like this. We have some collector resistance RC. Our output voltage V out is taken at the collector terminal. Our emitter terminal is grounded. And we apply our input voltage at the base. Okay, so this is common emitter, right? So any amplifier in which we apply our input signal at the base and measure the output voltage at the collector is a common emitter amplifier. Okay, it's called a common emitter because in its most simplified form, the emitter is at the common or ground potential. The next one is this guy. We take our output here at the emitter. We have some emitter resistance RE. We apply our input signal here. What do you think the name of this guy is? Common collector, okay? So the common collector amplifier has the collector at a common voltage. So right now it says it's at VCC. When we do our small signal analysis where we turn off all of our DC sources, that VCC looks like ground because VCC is set to 0. And so we would see that the collector terminal is at ground, so it's a common collector amplifier. It is sometimes also called an emitter follower amplifier. And our third basic configuration is the common base amplifier, where we have some collector resistance RC. We're going to take our output at the collector terminal. We're going to apply a DC bias voltage to our base. And we apply our input at our emitter terminal. So this is common base. All three of these are examples of voltage amplifiers. Okay, so rack your brains, think about where you were literally 1 year ago in circuits 2, when we were talking about voltage amplifiers in particular, like the op-amp. What were the 3 parameters that defined the behavior of the amplifier? Or any amplifier? Not the ideal op-amp rules or anything, the 3 general parameters. Input resistance, output resistance, voltage gain. Those are the same 3 things that tell us how all of our transistor amplifiers are going to behave. Voltage gain is fairly straightforward. We know that that is simply the ratio of the output voltage to the input voltage. I believe we've beaten that to death in multiple other classes. Okay? We will go through the steps of doing it, but I don't feel that I need to explain that quantity. Measuring the input resistance and measuring the output resistance of the amplifier might not be something that you're used to doing. You're probably used to having it told to you. Okay. So let's talk about what those steps entail. So if I have let's call this guy measuring input resistance, and I'm going to put in parentheses here impedance because I'm going to use resistance and impedance interchangeably here. So if we have a generic black box amplifier circuit, we have a pair of input terminals. So for us, that's usually whatever terminal we're applying the input signal, and then the bottom terminal is ground. We have a pair of output terminals. If we want to measure the input resistance, we apply here's Vs, here's, I'm going to call this V signal and R signal. We have an active or live network. We measure the quantity Vx, we measure the quantity Ix, and the input resistance Rn is simply the ratio of Vx over Ix. Our output for load terminals must be open circuit. This is how we're going to measure our input resistance. Pardon me. Measuring output resistance. Or impedance. If we have a generic black box amplifier, we are going to apply our test circuitry to the output side. So here's our signal. Here's V signal. We measure Vx. We measure Ix. And it's very important that our input terminals are shorted. So these are the rules for determining the input resistance and output resistance of any generic amplifier set. So as a quick example, let's look at what I'm going to call common emitter core without so common emitter amplifier, as a very brief review because we literally just covered it a moment ago. Is this guy where we have some resistor RC. We take our output voltage here. We apply our input here. Whenever we're doing our small signal analysis, and anytime we're doing the amplifier analysis, it's small signal analysis because these are small signal amplifiers. We are going to treat any and every DC voltage as ground. Okay. So if I were to draw my small signal model for this guy, it would look something like this. Let's make this terminal our base. Here is our resistance R pi. Here is our small signal voltage VBE. Let me make this slower. Here's our emitter terminal. GM VBE. Here's our collector terminal. So that's my transistor to begin with. All right. What else do I have? So between my collector terminal and AC ground, my power supply, I have the resistance RC, right? Since my emitter is at ground, I'm just going to use this whole thing as my ground terminal. Between my base terminal and ground, I have my input voltage Vn. And my output voltage, actually, let me move RC to the other side, is measured between my collector terminal and ground. So here's VI. So this is the jumping off point for our analysis here, our amplifier analysis, all right? So for all of these circuits, we are going to determine three quantities: R in, R out, and the voltage gain AV. So which one of those three quantities do you guys want to take a crack at first? R in. Okay. So how do we modify this circuit to determine R in? We don't have to do anything, okay? Our output voltage was already an open circuit voltage. All right, so what we are trying to find is the ratio of the potential difference between here and here, because those are the terminals across where our input is placed, and divide it by the current that's flowing from here to here. By definition, we should be able to do that by looking at this. Anybody have any thoughts? R pi, exactly right. So if we're looking for the resistor that we see between these 2 points, it's R pi. We're done. Rn is equal to R pi. All right. Capital R. I'm going to get myself mixed up. Okay. We want to find the output resistance. What do we need to do? So Vn is a short circuit. So if Vn is a short circuit, what's VBE? 0. So how much current is being supplied by our dependent source here? So what does it look like? An open circuit. So we're looking in, we have RC, an open circuit, and then a resistor that's shorted out. What's our output resistance? RC. Right, let me redraw it real quick. So if we shorted this guy out and then drew a set of terminals that we were looking in through, when we know that this guy is 0, we see RC in parallel with an open circuit. So it's just RC. All right, so our last parameter is our voltage gain. Right? So the voltage gain by definition is simply the ratio of V out to V in. I would argue that V out is equal to negative GM VBE times RC. Anybody care to either agree or dispute that? All right. So I got there by saying the current that's flowing into the negative polarity terminal of V out is GM VBE. And from Ohm's law then, V out is GM VBE times RC, because the current's flowing into the negative polarity terminal and the negative side. Literally circuit to one level analysis here. All right. Gregory, what's the relationship between VBE and VN for this particular circuit? They're equal. They're the same thing. So our voltage gain, which is just V out over V in, is negative GM . Congratulations, you've just done your first transistor amplifier circuit. It only gets harder from here. All right. We've got about 6 minutes left. Let's call it a day for today. We'll throw the early effect in here when we start things off, I guess next Friday, is that right?